Hi everyone, my name is Emmanuel, and together with Frederick, Joseph, and Richmond, we model the dynamics of seasonal flow with vaccination. Some basic ideas about this model. This model represents an extension of the basic SEIR model, where we added vaccination into the system. The model also represents the spread of respiratory illness, and specifically, we were looking at the spread of um, seasonal flu virus. The model also represents a general population, just like Vermont. Um, and we have a couple of motivations about this model. Um, One was to explore infectious disease modeling with open population by taking migration into account. And the second one was to explore how vaccination and isolation affect the dynamics of our model. We also have several assumptions on this model. The first assumption was that the population is divided into 5 compartments. The second assumption was that our model represented deterministic homogeneous mean field approximation. The third assumption was that the system is open. The total population can change due to immigration and disease-induced death. Our fourth assumption was that migration grows logistically with some carrying capacity. And we also assume that individual in the system, once they recovered, they can be susceptible again, go to a susceptible compartment. And our last assumption was that transmission rates are normalized by the total population.
Okay, here is our model diagram, specifically a compartmental diagram. As Emmanuel said, we extended it to vaccination, so you can see the extra state variable V. And we also introduced logistic growth through migration. So healthy people are allowed to come into the system at a rate M, and we considered healthy people S and V. And this migration is capped by the total population, which you can see as 1 minus N over K. The rest of the system, you can see kind of is your standard SEIR flows, but one difference that we added was we normalized our transmission rates. So we did that by introducing the total population and putting that under I, and that creates a probability that we can multiply the AS by or the EV by. And then some other parameters. We decided G was an isolation rate. There's a lot of U's coming out of these compartments. You can think of that as emigration. You can only die if you're infected. That's where the J comes from. And the I means once you recover, you can get sick again, which means you go back to S, which gives you the potential to get sick. And then D is the latency. So once you get exposed, how fast do you move to infected? Also note that you have to interact with I to get to E. Just because you interact with I doesn't mean you go to I, which is also something to note. And then here are the equations. Like we saw in the beginning of the semester, these are ordinary differential equations, a system of 5 of them, each one representing a state variable. You can see the logistic growth term in the first equation, the M, S plus V, 1 minus N over K. Things like CV and IR just a parameter connected to a state variable. That's going to be exponential growth or decay. And then you can see we have a couple of nonlinear terms with the state variables multiplied together, like the SI and the VI. That's interacting terms, which those are the only ones that are getting normalized with that over the total population there. And then we needed to say it at the bottom here that n was just the sum of the state variables at any given time. Definitely we're using the total population a lot in our model to guide us. And then we were going through the parameter sweeping and just trying to find graphs, and we thought of these three scenarios that we were that kept popping up. So like the disease dies out, or it kind of enters an equilibrium. It doesn't die out, but it does like stabilize to a value. Or the total population actually just dies out and there's no disease or no population in general anymore.
So now, jumping off of the scenarios that was presented by Joe, we can now look at the results. So in panel A, it sort of depicts our traditional SEIR model, which is our base model. Here we can actually tell that the number of susceptible populations decreases as infection rates increases. And at a peak of infection rates, we realize that the number of recovered patients begins to increase over time. If we move to panel B, when we introduce migration rate, we realize that with also an introduction of vaccination into the model, you realize that the number of infections decreases over time. But then we see a sharp increase in the vaccination rate, the number of susceptible population decreases, infection rate decreases, and then recovery rate increases over time, gets to a peak, and also slowly begins to fall, but it doesn't fall over time. Now we move on to the other scenario where we sort of model our model without immigration rate. Here we realize that keeping vaccination rate constant, again, the number of susceptible populations fall. Infection rate takes time, but after about 200 days, it gets to its peak and begins to fall. The number of recovered people in the population increases over time, gets to over 400 days, and begins to stabilize at that point. If we move on to a situation where a policy is implemented, which is self-isolation or a movement stop order in the system, we see an interesting results popping up. Here, what we can actually observe is the number of susceptible people falls drastically, and then levels of it doesn't go to zero, or it doesn't goes to zero. But then we see an asymptotic decline of those who are exposed and those who are infected, and again, those who recovered. This dynamic is very, very interesting because we expected that when there is a movement stop order or there is an self-isolation imposed in the system, we should expect that the number of recovered people should increase. But then we observe that it's very, very asymptotic, which is probably closer to zero. A possible explanation could be that there is some deficiencies within the ODE model, such as it doesn't look at interactions between agents. So probably examining this model critically through the lens of a network model or an agent-based model would help. We now enter into the last phase of our simulation exercise, where we see that the disease enters into an equilibrium with an oscillatory pattern. So in this case, the number of vaccinated people, all of these things, all of these parameters follow an oscillatory pattern over time. And we also see that when the recovery rate increases by a certain threshold, we begin to observe this oscillatory pattern. An implication is that when the system is open to migration, we are likely to observe some interesting patterns within our model. With respect to the last panel, which is panel B, when we increase death rate by a certain fraction, all we could see is, yes, initially the population, the total number of population falls a little bit and then rises again and gets to its carrying capacity. What is interesting is the number of recovered patients continues to rise and then levels up at a certain point in time. Exposure to the disease as a result of an increase in vaccination falls considerably. And again, we see the number of infected people also falling considerably. So Fred will present a summary of our findings.
So in summary, our baseline model follows a traditional SEIR model, which is some sort of validation for a model. And we realized that introducing high vaccination rate into the model limited infection and exposure. We can also observe that leaving the system partially open will result in an uptake of population to some carrying capacity, whilst your infection will drop significantly. If you have a small group of people coming into your system with a strict quarantine order, infection reduces significantly, as some of our graphs showed. And with an increase in immigration, the system enters equilibrium through oscillatory patterns. And finally, we can also say that with an increase in death rate, there is a sudden uptake of infection before the disease dies out. So what we have done here is to take an SVER model and try to study the behavior of this model when it is an open system. And we realize that our model parameters are very sensitive to perturbation. And because our model has many parameters, we can observe other behaviors in our system, which we couldn't get enough time to do those observations. And this model can be improved when we consider interactions between agents through the lens of network or agent-based model. Thank you for listening to our presentation.